So coming to our session today, yesterday we completed till the layer class and we implemented a single layer of neurons. So from single neuron, we understood how we can switch to multiple neurons and multiple neurons in a single layer. So up to that point is what we implemented yesterday. But that doesn't fill the entire artificial neural network because we have to work with multiple layers. So it's multiple neurons in a single layer and many such multiple layers. That will form the entire neural network. And moreover, what we completed yesterday was only a forward pass. So we did not calculate the loss function, we did not calculate the loss value. After calculating the loss value, we did not correct our weights and biases which can be tweaked. So today, we'll cover two things, that is introduction of multiple layers and calculation of the loss value. Today, we won't be correcting our weights and bias, tomorrow we'll be correcting them. So today, we'll complete the backward pass and calculation of the loss value. Up to that point is what we do today. And the reason I kept this window open is I wanted to show you there is one notebook, DL Students Week 2 Day 3 Practice Notebook. So I want you all to please fetch this notebook. The reason I am giving you this notebook is because I made few changes in the value class. So there are some other operations which we did not introduce yesterday or until yesterday. Example is d_power method, which we did not use so far. But that's going to be useful for exercise 1 and 2. That's the reason I'm giving you that code. Again, it's very similar to what we implemented, what all functions we implemented so far. So it's no brainer to have an exercise on it. That's the reason I'm giving you the code. You can use it. And drawdot function is also there in the notebook. Additionally, I gave you the neuron class and the layer class, what we implemented yesterday in the notebook. So I can do a quick fetch and show you. So as you see, there is a drawdot method in the first cell, the value class, and this is the additional method that I talked about, that is d_power. This is to...
SRIPOOJA, your screen is freezed.
Thank you. So this is the other method that I included, d_power, to handle the power operations, mathematical power. And additionally, there are some other methods like radd, which you implemented yesterday, rsub, rmultiplication, true division, rtrueDiv. Neuron class is what you implemented yesterday as part of exercise 1 and layer class as part of exercise 2. So up to this point, whatever we did yesterday, I made sure it's there in the notebook. So today we begin with MLP class. So I'll switch to my view. So up to this cell is what is there in your notebook. You can see this output if you run it. Now this is the visual representation. So this is the visual representation of how the classes are nested or how they are dependent on each other. So you can think of MLP as a super wrapper over all these classes. MLP has a dependency on layer, layer class has a dependency on neuron class in turn has a dependency on value class. So far we implemented up to layer. MLP is what we are going to introduce today. So we'll be implementing that now. But before that, there is one more diagram here. So this is my target, or this is the goal that I want to implement as part of this short in-class activity. So what does it say? I have to implement an MLP class, and this should be able to handle multiple layers, and it should be able to implement a neural network of this dimension. So clearly, we are taking 3 inputs, that is x1, x2 and x3. Then there is another layer of neurons of size 4, that is, let's call it hidden layer 1. There's hidden layer 2 which has 2 neurons, and there is one final output. So this is how I want the MLP class to generate a final neural network. So let's see what can be done. But before I implement the MLP class, let me design how my MLP class should be taking the parameters or values. So clearly from this diagram, I understand there are 3 inputs. So please code along with me. So x equal to some values. I choose to take 1, 2, 3, just so that the values that we are calculating remain small. So this sums up the x1, x2 and x3, and then I want my MLP class in such a way that it takes this 3 inputs, right?
Yeah, SRIPOOJA, can you zoom a little bit? And what is this exercise? Is it a notebook?
This is a practice notebook.
Practice notebook, right?
They have access to it. So we are taking 3 inputs, 3 x values, and I'm saying this MLP class, whatever I'll be implementing, it should be able to take the dimensions of the input. So that is done. Now, the remaining part of the neural network is the dimensions of this layer, the layer 1, hidden layer 2, and the output layer. Now that I have to define here. This is how I choose to define or implement my MLP class. So I am saying here there are 4 neurons, 1, 2, 3, 4. So I say 4, and then 2 neurons in the second hidden layer, this is 2, and the final output, or if we call it output layer, then it is 1. So basically my MLP class, which is going to create a neural network, will be able to take or should be able to take 3 inputs. Then it should have the following hidden layers of size 4, 2 and 1. Done? And then this is only the init step, as we all know, init of NN. Then we have to do a forward pass. So forward pass of NN. So for that, I have to pass the input. So n of x. So whatever class I will be implementing should be able to handle all this data of this type. So this is the calling part, but the implementation is still not done. So I will introduce one cell above this cell, and I'll start implementing the MLP class here. Class MLP. So first what I'll do is init layers, right? So this is a d_init method which will be taking self by default. And here what do you think should be the value? How many arguments will it take? So I basically told you this is how I would like to have my MLP class initialized. So how many arguments should be there here? 2 arguments. So if we remember from the previous example or the previous implementation of layer and neuron, we chose this naming convention, NIN and NOut. So I'll use the same naming convention so that it becomes easy for us to understand how data is getting exchanged. So NIN to represent the number of inputs, and then NOut. So in this case, it is not just one output, it's multiple outputs. So instead of saying NOut, I will name this as NOuts. Okay? And why is it NOuts? That is because we have multiple output at each layer. So if we consider hidden layer 1, this node is connected to 4 outputs, whereas this node is again connected to 2 outputs, and finally it goes to 1 output. So that's the reason I'm saying it is NOuts, not a single output layer. Now we have to define the size of layers. So for that I will say SZ, and here comes slightly tricky part. You have to understand this very clearly. So NIN, what we are passing here, is an integer value. So I am saying we have to combine this and this list somehow. Now since this is integer, I am using the square braces to form a list out of it. A list with only one value, that is NIN. And then, since this is a list, I can now concatenate both the lists, NIN with NOuts. Why am I doing this? In the next step, you will understand. And now, because the initialization of NIN and NOuts is done, the size of the layers somehow is there in a list. But the main goal, that is initialization of layers, is not done yet. So let me call it layers here. So I choose to call this attribute variable layers, which is a class variable. And here, it is going to be a list of which class instances? Layer class, correct. So layer. Now what does layer take? If we go back to our layer code, you can see it takes n in and n out. So let's say for the first iteration, that is for this set from x1, x2, x3 to this 4 neurons. For the first call, what do you think should be the values? Should it be 1, 2? Should it be 2, 3? What are those values? Yes, NIN? N of? N outs of 0. So in integer, can you tell me what is that? The variable names you're giving me correct, but the values? 3, 3, 4. Okay. So that will be this layer, right? Up to this. Now what about the second iteration? From here to here. 4, 2. And then 2, 1. So 3, 4, 4, 2, then 2, 1. So for that, what I do is, I would like to use the same SZ list, the size list. Okay? So I'll change how I do the indexing here. So I will say the first element, then the corresponding second element, plus 1. And why will this work? Because I will say for I in range, length of, what do you think this should be? Size? Are you sure? Edge case, will it work? I have I plus 1. N outs, correct. So if I take it as length of size, that is SZ list, then this case will fail here because I will be crossing the boundary, the last index of the last element. So it has to be N outs. Okay? So this is the implementation logic. I will show you along with print statements why this is working. So let me comment this code for some time. Put it in another cell. So basically, I just want to check if the implementation is going correctly or no. I will check how many layers are getting initialized. So now MLP is this. I'm not returning anything, init doesn't return anything. Now I want to verify if this is correctly getting initialized. That is, the layers are getting correctly initialized or no. So there is an error, layer is not defined. That's because I did not run my previous cells. In your case, I think you should be able to see the code. Right. So when I run all my cells correctly, the layer class is initialized. If you run that cell, you should be able to see a list of 3 layers. And why 3 layers? Because this is hidden layer 1, hidden layer 2, and 1 output layer. Though this is called input layer, many people have a slightly different opinion that this input should not be considered as a layer at all. It's just input. So you treat it as input, but don't call it layer. This is hidden layer 1, hidden layer 2, and output layer. So now we have initialized 3 layers, right? And now why is this logic working? You might be wondering. So what we'll do is, we'll just print what's happening here. So I'm saying for I in range, len of n outs. So let's see how it's taking the values. Now print. So I just added this print statement to see how it is working and why. Okay, so I missed the flower braces here. So you can see here, now for the first layer, n in is 3. Correct? That's because x1, x2, x3 for the first layer, this is the input. And what is the output? That is 4 neurons. So this is composing my first layer. Now for the second layer, it's taking 4 inputs. And where are those coming from? It's coming from the first hidden layer. So that's the reason n in is 4 and n out is 2, because hidden layer 2 has only 2 neurons. And for the last layer, that is the output layer, it is taking 2 input and it is generating 1 output. So that is why it's working. This code is working precisely for that reason. So whenever you're getting confused, you can include few print statements to check why the code is working. So all good up to this point. Now after this, we just initialized the neural network. So NN init is done. But what is missing? The forward pass is missing. So let me take some x values here, which I initially thought, that is x equal to 1, 2, 3. So this is my input data. And now I should be able to pass this to my neural network. But do we have the logic to handle this? Not yet. So we have to add that logic here. So def, the callable method, as we used in layer class and neuron class, we still use the same method. Self, comma, this time what should it take? X value, correct? So I will name the argument as x. And now what do you think should happen? Logically, we have layers, we have input. And how do we call the forward pass? Should it be on all layers or should it be on single neuron or how? One after the other of what? Layers or neuron? Layers, right. So we have the code already equipped to handle that up to layer. We are able to pass this. So somehow we should be able to call n of x on the layer, right? So now coming back to our MLP class, we have to iterate over the layers we have. So for layer in self.layers, whatever we initialized, and then again there is a slight trick in the code here. I'm using the same variable name, the same name. See this closely, x equal to layer of x. And I will say return x. So what do you think is happening here? So I'm taking x as input, then I'm passing it to the layer. What does this return? This is the final output? No, intermediate output. So output from layer 1. So it's getting overwritten here. Now for the second iteration call, it will go to this layer. And so far, finally it will go to the final output and this iteration will terminate. So what we are left with is the final output, right? So this looks simple, but you have to understand very closely, like why are we overwriting the variable names? Why are we reinitializing them? Otherwise, you will not understand how to debug the code. So let's see whether this works correctly as we expect or no. So for the forward pass, I have my input data ready and I have to initialize this and call it. So I can see some value here, which is the output from the output layer. Now if I rerun this, generate some other output, that's because we are using randomization. And where is this randomness coming from? Random.uniform. In which class? Neuron class, yes. And if we have to control this randomness somehow, let's say you want to check the code in your NN, whether it's working correctly or no, you can control the randomness by using the random seed and you can set it to 10. In my case, I would like to set it to 10 and I see this value. So if I rerun the cell again, I see the same value. So that is how random seed also helps you in debugging your code. Because if you start at a random state, if you plan to debug your neural network to understand why it's underfitting or why is it overfitting, randomness will not help you. So that's the reason you have to control the randomness until you fix the overfitting or underfitting problem, and then you can introduce the randomness again. So this was all about the MLP class. So I think we are good for exercise 1. We can get started with exercise 1. And for those who missed submitting exercise 1 yesterday, so I have some code snippets that you can fill in today. So it's going to be like a recap for you. I'm providing you the value class directly as part of exercise 1. but you have to fill in the code for neuron class, layer class, and also the MLP class. And then there is a draw dot method, which is already there in the notebook. So once everything is done, you initialize the neural network, just make sure you run the draw dot once and see how humongous is the graph now. Okay, and give me a minute, I will open the notebook. So I think you should be able to see this notebook now, which is named as week 2, day 3, exercise 1. And the exercise reads as forward pass using MLP class. So in this, I clearly mentioned that you have to implement neuron, layer class and MLP class. Value class, draw dot are defined. And now what are the dimensions of the neural network? For that I gave you a picture. This is so that you understand how to read a neural network architecture and how do you convert that into numbers. So that was a short exercise I want you all to do as part of this assignment. So you can refer back to this picture, and if you scroll down further, you can find the neuron class. The signatures of init and call method are here. You have to fill in this one, and you have to complete the layer class implementation also. Then MLP class implementation, you have to do whatever you did during the live code session now. And the input value is already predefined. So make sure you don't change the seed and you don't change the input. If you change either of them, then the visible test case will not pass. And once your code is logically correct, if you're confident, then the hidden test case must also pass, where I'm using slightly different values and different network architecture. So this is all about the assignment. So if you have any questions or if you're facing any issues in submitting your notebook or not receiving feedback, please let us know upfront. 15 to 20 minutes and not more than that.
Just comment that out. Don't submit. While submitting, please comment the line draw underscore dot. Yes. If you are facing problem, please let me know. 80 submissions is fine. If you are still submitting, submit it. You closed it. So please submit it within 2 minutes. And don't worry if you don't get the feedback, because meanwhile we'll just click on this evaluate, it comes up. Yeah, you ready for the next? Yeah. Yeah, the next is that. Anybody facing any issues? Yeah. Please raise your hand who is facing issues. I have a question here. You see the multi-layer neural network, correct? Why 2 layers? Why many neurons? Why do we use that? What are we trying to do here? What's the final output? What we are trying to achieve? Anyone? You're learning 2 hidden layers, correct? If I use only 1 hidden layer and 2 neurons, what is the effect? Pardon? If you want to talk, please raise your hand so that I can come over to you. My question is, if I have only 1 layer and 2 neurons, 1 hidden layer and 2 neurons, what is the final output effect? What happens? No answer? Please raise your hand because I want the name. Okay, no problem. Let's see what happens. By end of the class, I'll again ask this question. I hope you will come up with the answer. Okay? Yeah.
You should have seen that now whatever we did so far is generating a humongous graph. We earlier dealt with small mathematical equations. Now that is getting translated to a huge graph. See, so many layers, so many operators. So it's all the code that you implemented until today. So this is giving the complete neural network. But there are a lot of missing pieces here because we are not filling the gradient value yet. We somehow have to fill that gradient value. We do not call the backward so far. So, but this is to give you a visual representation. So I'll clear this output. And now, here comes the second activity, that is in-class activity. So we close the exercise 1. So if anyone is still working on that notebook, please don't do that. Stop working on it. Please focus here. So here comes the second in-class activity. So what are we going to do here now? There's a small fix that we have to do in the layer class. We'll do that later. First, we'll try to create a tiny data set, right? Usually, we get the data sets readily available. We download it from Kaggle. Then we do data processing, somehow convert them into numbers. But today, we'll create and initialize a small data set to begin with. And we'll also initialize the truth labels. So what are my x values and what are my y values that I'm going to initialize. So this is a small code that I kept ready. So you can also initialize the values of your choice on your notebook. I'll give you 2 to 3 minutes because it will take time. But make sure that the dimensions are same. So each input list or each record has only 3 features, right? X is XS or the X's has 3 features in each record. Has 3 features in each record and it's finally generating 4 outputs. In-class activity. Done? So basically I was looking at few of you are doing like this, up, down, up, down. When that's done, I'm assuming it's done. So you initialized it. So this is good because we have the features and then we have the ground truth labels. So we'll call this the ground truth labels because these are the labels assuming it's coming from a data set. So ground truth labels, okay. Now the prediction. This part is not done yet, right? We have a data set, we have labels because this is a supervised learning setup. We have a neural network. But where are the prediction values? How should we get it? Sorry, louder please. Forward pass, okay. So if we take a look at the previous cells, we initialized our multi-layer perceptron. So what should we be calling here? For each XS, okay. So tell me what should be my code? N of X, okay. But where is this X coming from? From XS, for X in XS, okay. So let's see this and what is the length of ypred should be? What do you think should be the final length of ypred? 4, right? And that is because we have 4 records in our input data set. That's the reason we should be able to see 4 outputs, 4 corresponding outputs. So let's see if it's correct, right? So this is fine. So it's giving me a nested list of multiple outputs, that is 4 outputs. So I have 4 records, I'm passing that to my neural network. It's doing a forward pass using each record and then it's generating 1 corresponding output. So did you all generate this, the final output? Okay. Now, this is fine. So the forward pass is done. Till this step, forward pass completed. Now what else is pending here? Backward propagation. But when does the backward propagation begin? After calculating the loss. So we have to calculate loss. And for this, I choose to use mean square error because it's easy to use and easy to understand. So I will choose mean square error as my loss function and now I want to implement that loss function. So loss equal to, so what should it be? Sum of y's, but how? Where's the difference? Ypred minus y's, okay. So I'll choose different names. So first is my formula. I will say y out minus ygt whole square. And where are these coming from? For y out, comma, ygt in zip. because sequentially I want to do it on pairs of ypred and ys. So y out is for ypred. For me, ypred, and then ground truth. Ground truth is coming from y's, because this is along with the data set I am receiving. So fine. Now let's also print the loss value and see. It will throw an error. So where is this error coming from? I mentioned that in our in-class activity, we have to do a small fix in our layer class also. I'll show you what is that fix, but tell me where is this error coming from? Which class or which line of code? Value class? Are you sure? But there is no value involved at all. It says list and float. Value is becoming list. Layer is returning list. So there has to be a quick fix in our layer class. So where is layer? Yes. So basically I am returning outs, that is list of output values. So I will say you return only the first element if there is only one output. So you return outs of 0 if length of outs is equal to 1, else return outs as it is. So make sure after you implement the loss calculation, come back to the layer class and change the return value in the callable method. Instead of returning outs directly, just check if the length of the output is 1. In that case, just return the first element. Else, you return the complete list. And today in our exercises and for the in-class activities, we just generate one output, not multiple output. So this code will work fine. So if this is done, the next step should be to running these cells, because remember the initialization happened with the old layer class. Now because I did the changes, I have to rerun all my cells. Draw dot is something I don't want to run. So next is this and this. So finally it's generating some loss value. And for those who could not understand what happened in the layer class, I'll show it to you again. So in the layer class, we modified the output. This line of code is what we changed. So instead of returning list, if there's only one element, we are returning that element. If there's only one output coming out from that layer, that is for the output layer case, if there is one output, we return that last output, the element in the list. Else, we return the complete list of outputs. So why are we doing this fix? This is because we don't want the loss function to throw the error, and if the list value is not equal to 1, that is if the length of the list is not equal to 1, it will normally return the output. So for your hidden layers, that logic will still work. Now the loss calculation is happening and I see 6.1244 is the loss value. And what is the next target that we have? We calculated MSE loss, fine. Now we have to collect the parameters. And what do you think when I say we have to collect parameters? We call hyperparameter tuning, parameter tweaking, or hyperparameter tweaking. So what do we refer to in that case? Learning rate, okay, that is one of the hyperparameters. Besides that, consider only what we implemented so far. With whatever implementation we have done so far, what do you think are the parameters that we are holding? In the neuron class, in the layer class, in the MLP class, what are the parameters? Because learning rate, gradient descent, correction of weights and biases, we did not do that yet. Weights, yes. Parameters, definitely weights, and also the bias. So why are we doing this collection of parameters? Where do you think it will be useful? Why should I know my parameters? To change, updating them, okay. Yes, he's right. So basically we should know how the parameters are getting updated, because that is something which happens automatically if you're using PyTorch or if you're using TensorFlow. But remember, we are doing a complete decomposition of these libraries by implementing our own classes. So we want to understand even at the parameter level how they are getting updated. So today we won't be updating them, but I will show you how we can get a complete list of the parameters, so that tomorrow when we are doing the gradient descent, you can take a look at the parameters, how they are getting updated. In each iteration of your learning rate, how you change it, and then each epoch, how does your parameter change. So we'll see that tomorrow, but today let's keep our classes equipped with all those methods. And now my next target is to collect the parameters. So you said the parameters are there, they are weights and biases. So where do you think we have to implement this method to return the weights and biases? In which class? In value class, do you think we have to return something? Okay, in which class are we initializing weights and biases? Neuron class. So certainly there are parameters there in that class. And again, is there any other class which is using those parameters? Layer is using. And what about MLP? MLP is also using them, right? So we begin with neuron class where the parameter initialization starts, and then the other classes which are using this neuron class internally also have parameters. So we keep pushing it one class by class, so that finally when we call the parameters method, we can list the complete parameters. So let's see how we can do it. So I will go to the neuron class directly. So neuron class is here, and I want to call this method as parameters. And this takes self because it's a class method. So my expectation is that by implementing this parameters method in neuron class, this method should return all the weights and biases in the form of a list. So what do you think my return statement should be? So it should be a combination of weights and biases in one list. So return of, do you want to fill it? Yes. Okay, so we have weights. And how do I pass the bias also? Remember, weights is a list, bias is a single value. Square braces, correct? So I choose to go using this syntax, which is self of B, and now as you mentioned, a square braces. Because self dot B or the bias is only a single value. I want to concatenate both. So now this returns all the weights and biases in the form of a list. Up to neuron class, this is good. So done. Now coming to layer class. Now layer class also has to pass this to the next class, which is MLP. Because remember, from MLP we are coming down. From this diagram, if you see, where's the diagram? Yeah. So MLP class is what you're dealing with to pass the input and call the forward pass, backward pass. So MLP, layer, and then neuron. So value class is not in picture right now. Neuron class has the weights and bias. So this has to send the values to layer class, and from this it has to be sent to MLP. And when we call something, the parameters method on MLP, we should be able to display that complete list. So we fixed our code, or we implemented the code for neuron class. Now it's time to modify our layer class. So we'll use the same method name, def parameters, which again takes self. And what should this return? This should also be a list. But what should the list contain? Because the layer has only neurons. So how do you think we should dereference neurons to get our list of parameters? Iterating for each neuron, okay. So going by what you say for neuron in self dot neurons. So here what do you think should be there? So can we do it here or we need to iterate further? Iterate further. Okay, so one more nested for loop. Now I choose to have it in line, in the same line. So for, I will say P in neuron dot parameters. Because remember, we implemented this parameters method here, which is returning a list. So basically here, now that the neurons are initialized, I am iterating over each neuron and calling parameters method on each neuron. That's the reason why this is going to work logically. Let's see. And now I have to return P. And where is this P coming from? It is coming from here. For parameters, in a single neuron's parameters, keep appending those values. That is what it means. So this is going to work at layer level. So make sure you have this code implemented. I will give you 2 more minutes. You can also try with print statements because you have layer class, MLP class. Just print and see if the parameters are getting returned correctly or no. The same method again, the same name, parameters itself, and return this time parameters for, in this case how do we iterate? Because what we have is layers. So let me copy the code that we implemented in the layer class, then we'll see how it's similar or how it's different. So this is what we did in the layer class. Now this is MLP. So it should be same, but instead of neurons, we will be dealing with layers. So for layer in self dot layers, for, yes, P in, correct, layer dot parameters. So this is a method call. Now this worked for layer class, and whatever we did not comment, it is for the MLP class. Enter. Now again I have to initialize my MLP because I changed the class code. Good, so it's giving me the same data output now. Again coming back to this tiny data set that we created, let's calculate the loss. It should still be the same. Yes, it is same. And now we did calculation of loss, this is fine. But how do we print the parameters? We collected them, we are assuming that the collection is happening correctly, but we did not make a call or we did not invoke those methods yet. So how do we invoke those methods? N dot parameters. N because N is where we are initializing our neural network. Where is this step? Okay, so here is where I'm initializing the neural network. And after passing all these values, now I'm checking what are the parameters. So let's print this and see. So it's giving me a huge list of parameters. And let me print the length and check what's the length of the parameters. Length of N dot parameters. So it has 29. Same at your end? Okay. Now what we'll do is quickly we'll go back to our MLP where we initialized. We'll change the dimensions of the layers. This time instead of using 4, 2, 1, let's say we use 4, 4, 1. Okay? So I'm just changing my architecture of the neural network. Instead of using 4, 2, 1, 4, 4, 1 is what I'm doing. Now let's see if it has any impact on number of parameters or no. Good. This loss function. So my loss value has changed slightly. Now the parameter list also changed. Now it looks lengthy. And let's print this. Earlier it was 29 for 4 to 1. Now it is 41. So just because we are increasing the number of neurons in a layer, the number of parameters have increased. So similarly, you can play with this code and understand how it's working. Now forward pass is done, loss calculation is also done. What else is pending right now? Back propagation, yes. So how do we call the back propagation? What do you think? How should we call the backward propagation? Back propagation, do we have a method to handle that? Backward, yes, but how do you call it? And where is your backward method? Is it there in the MLP class? Value class, it's there. But what is the type of n? Type of n is MLP. So there's no backward method there. So which other variables do you think have this access to backward? So I'll give you a hint. We have couple of variables here. X's, Y's, Y-pred. Then you have loss. You have n. So on which variable do you think backward method will work? Out of all these variables, which one is of type value? X's, Y's, Y-pred, loss, n parameters, loss. Right, so this is of type value and that too a single output. So let's call backward on loss and see what it does. So this is taking it. Now let's print the n parameters again. Just remember a top few, these were from the previous run. So this had dot 142 and 142 here negative. If I rerun this, let's see if it changes or no. So it's still the same. So data is still the same, but did you notice, is there any change or no? Is there any change or no change at all? Is there any update? Grads, right. So I was intentionally checking data just to tell if you were pointing me at grads or no. Because by mistake, I had put an assertion on grad today in your exercise 2. And I was wondering why is this not passing after calling backward. That will change every time, right? So then I removed it. So we are successfully able to call the backward and we notice that the gradient values are changing. But the weights and biases we did not update yet. We'll do that tomorrow as part of gradient descent. And tomorrow, to give you a heads up of the exercise, it's going to be a accumulation of whatever you learned from day 1 until today. Plus the gradient descent, what we'll be learning tomorrow, exploring tomorrow. So expect a jumbo exercise. Maybe we can plan one or one small and one jumbo exercise. So be prepared for that and please inform your friends also because we are going to consider this, the weightage of tantric exercises, whatever you score, that will be added to internal exams. So please inform them, ask them to come, attend the classes and also take the exercises. You don't do the exercises for them. So this is till the backward pass we completed today, but tomorrow in depth I'll show you how we can use this backward call and how we can update the weights and bias with the help of the loss function. So we'll be exploring the learning rate also tomorrow. Now since this is done, if you're facing any issues, let me know because in the next 2 minutes I'll be opening the second exercise. So if you do the second exercise, we are done for the day, you can leave. So if you're facing any issues, 2 minutes is the time, please let us know. And if anyone faced any issues with exercise 1 related to random seed, please raise your hand. How many do we have who have this issue? Exercise 1. You're hesitant, you had an issue with the random seed? Yesterday also few of you reported that randomness may be an issue. Is it resolved or no? Okay, so give me a minute, I will enable the second exercise, which is named as MSE loss calculation and parameter collection. So whatever we did during the live session, it's somewhat similar. But again, the network architecture is different in this case, which you saw in exercise 1, it's the same. There's only one visible test case. To give you a walkthrough of the code, you have draw dot method, you have the value class. And also please make a note of changes that I did to the value class. I included few other methods. Please understand them, why they are there, and if you remove those methods, what happens. After value class, you have the neuron class. Neuron class, I implemented the code for init, for the callable method, but you have to implement the code for collecting parameters. And the same goes for layer class as well as for MLP. So in neuron, layer and MLP class, you have to fill in the code for collecting parameters. And then finally, you have to initialize the MLP correctly. And then I have the X and Y values already initialized. You can make use of those values and generate the loss. And there is only one visible test case, and I split that into 3 parts. I gave you how I split it. The reason I'm awarding only 5 points is I wanted to make sure that the random seed is not causing any problem. That's the reason I reduced the weightage of these 2 assertions.